Hello, dear students, and welcome back to another fascinating journey into the world of chemistry. Let me ask you something. How do scientists manage to study more than 100 different elements without getting lost in their complexities? The answer lies in one of the most powerful maps in science, the modern periodic table. This is not just a chart stuck on your classroom wall, it is a story of order within chaos. According to the modern periodic law, the properties of elements are periodic functions of their atomic numbers. Yes, not their masses, but their atomic numbers. This simple shift, from mass to number, changed the way we study matter forever. Now, here's the real beauty. The periodic table is not just random arrangement, it correlates beautifully with electronic configuration. Imagine filling electron shells one by one. The K shell can hold 2, the L shell 8, and the M shell 18. In the very first period, we find only hydrogen with atomic number 1 and helium with atomic number 2 because only the K shell is available. Move to the second period, lithium to neon, and now we see electrons filling up to the L shell with a maximum of 8. In the third period, sodium to argon, the M shell comes alive with up to 8 electrons. What you are actually seeing on screen is how nature builds elements step by step, shell by shell. Isn't that elegant? This correlation makes the table logical and predictable instead of being just a list of names and numbers. Now, let's talk about groups. Look vertically down the table. A group is nothing but a family of elements with the same outer electronic configuration. That means they share the same valency and therefore similar chemical behavior. Think of the alkali metals lithium, sodium, potassium, rubidium, and cesium. Each of them has a single electron in their outermost shell. That one electron makes them behave alike, reacting vigorously with water, forming hydroxides, and releasing hydrogen gas. So, whenever you know the group of an element, you can almost predict its properties. Isn't that like having a cheat sheet for chemistry? But chemistry is not just about families, it's also about journeys across a row called periods. Move horizontally across the table, and you'll see the atomic number increasing step by step. With each step, electrons are added to the same shell and properties change gradually. For example, in the third period, we start with sodium on the extreme left, a shiny reactive metal, and end with chlorine on the extreme right, a greenish yellow poisonous gas. The same row contains metals, metalloids, and nonmetals, showing a clear transition. This is why the table is called periodic, because properties repeat at regular intervals. Take a closer look at the table again. Notice how neatly metals, nonmetals, and noble gases are separated. All the shiny, malleable, and ductile metals like sodium, magnesium, and calcium sit comfortably on the left. Nonmetals like oxygen, nitrogen, and chlorine stay to the upper right, showing very different properties. The central block houses the transition metals like iron, copper, and zinc, known for their variable valencies. And finally, the extreme right column, that's where the noble gases live: helium, neon, argon, krypton, xenon, and radon. Completely inert, almost like silent spectators in the theater of chemistry. Isn't it wonderful how one table brings order to such diversity? One of the greatest gifts of the modern periodic table is its power of prediction. Properties such as atomic size, valency, ionization energy, and electronegativity show repeating patterns known as periodic trends. Why does this happen? Because the electronic configurations repeat at regular intervals. For example, lithium, sodium, and potassium, though far apart in the table, all have one electron in their outermost shell and hence show strikingly similar behavior. This predictability means that if we discover a new element, We can guess much of its behavior just by placing it correctly in the table. Isn't that the kind of foresight every chemist dreams of? Now, even the most brilliant systems have their quirks. The modern periodic table is not without its limitations. The most famous example is hydrogen. Poor hydrogen doesn't quite fit anywhere. Sometimes it behaves like alkali metals with one electron in its outer shell, and sometimes like halogens, needing one electron to complete its shell. So, hydrogen's position is still debated. Another limitation is the placement of lanthanides and actinides. To avoid making the table extremely long, these elements are placed separately at the bottom. Yet, despite these small issues, the modern periodic table remains one of the greatest achievements in science, providing clarity and logic to the study of 118 elements. So, let's recap what we learned today. The modern periodic table is arranged not by atomic mass but by increasing atomic number. Its strength lies in its perfect correlation with electronic configurations, making it logical and predictive. Groups allow us to see families of elements with similar properties, while periods show us the gradual change across a row. Metals, nonmetals, and noble gases all find their rightful places, and periodic trends help us predict behaviors of elements we've never even touched. Yes, hydrogen still puzzles us, and lanthanides and actinides sit apart, but overall, this table is like a magical key that unlocks the secrets of matter. I hope this session helped you see how the periodic table is not just a chart, but the heartbeat of chemistry. Until next time, keep your curiosity alive because chemistry is all around you, from the air you breathe to the food you eat. See you in the next class.